type oscillation. And now we managed to bring it to Berlin in January 15 to 17. It's the MIA, Mathematics and Image Analysis. Some of you, I'm sure, have been there already as speakers, poster presenters, early career researchers. In particular, I would like to point you to this conference. Please check it out. And also the young researchers, as I understand, there's a PhD award, which even comes with the monetary reward as well, not just the honor of being decorated. And otherwise, yeah, please check out the webpage. If there are any questions, just contact me, Gabi, I would say in particular, and there are a couple of other organizers. I think I've said enough and would rather like to switch over to Antonin's talk. If I'm good enough with Windows, check. Yes, full screen. Okay, fine. All right, so now it's my pleasure to introduce the first speaker of the day, Antonin Chambolle. He's going to talk on convex representation for curvature-dependent functionals. And as soon as the information reconstruction has been done on the screen,
thank you.
Might be. Here it is again. Okay.
So
please just go ahead.
Thank you very much. So it's very nice to be here after some time. I will talk about a recent representation that we designed with Thomas Prof, who's here, for functionals on boundaries, essentially in 2D or lines, where there is a penalization of the curvature. And it will be a very simple penalization, but already we can outline a convex representation, which is nice. And also, this workshop is called Variational Method, New Optimization Techniques, and New Fast Numerical Method. There is nothing fast here. Don't really. You'll see. So, the idea, of course, the idea is vaguely inspired by the way vision is represented in your brain, by the way lines are analyzed in your brain, and it's based on the structure of the rototranslation group, but you don't really need to know anything about this to understand really the representation we have, which is quite simple. So I will first derive for just line energies with dependence on the curvature, a very simple formula to represent them, and then I will observe that this formula generalizes easily as a convex functional, which can be defined for 2D functions in 2D, and I will show or explain how you can show that it's a tight representation for very simple curves, for C2 curves at least. I will also show that it's related, of course this is related to, this will be in the next slide, to a lot of previous work based on the same idea, and in particular the formulation we find is in fact already found in a paper by Christian Thomas and Benedict Wirth, which however is a bit more complicated. So this one is already not very simple to optimize. I think previous one was even more complicated in some sense, and we'll show some nice results we have. Okay, so the first idea, maybe it would be good if I could draw some design. So. The first idea, which is now a bit standard for this kind of thing, is based on this way your brain interprets curvature, and the idea is very simple. You have receptors in the eyes, and these receptors are combined in a way to be sensitive to change of contrast, and this change in contrast has an orientation, like in every wavelet basis that you can rotate or whatever. So, and then the neurons which react to this orientation are stacked in a way and communicate, and they can detect a change of orientation. So the change of orientation is essentially the curvature, and that's how you can be sensitive to change of orientation. So this was observed, found by experiments in the 60s and 70s. And there have been a lot of mathematical developments, mostly by geometers who were trying to understand the related topology of the corresponding manifold if you represent a point by its localization and orientation. So representing a point by localization and orientation is essentially what is essentially using the structure of what is called the rototranslation group, which is a group of rotation and translation, where you have a point which is supposed to be a translation, and then a rotation which is like an orientation, if you want, and which is usually endowed with a Sub-Riemannian structure. So what is a Sub-Riemannian structure? So you have your point, you have your orientation, and the idea is that when so here, this is the rotation. You can parameterize this with the circle. When you are in a particular layer here corresponding to a particular orientation, you can essentially go only in one direction, which is specified by this orientation. So here my convention is that you will have an angle which corresponds to a tangent vector, and you will be able to move only in that direction. And here you can move in that direction, and etc. So it means that you have a Riemannian metric, which is essentially the standard one, except that it's plus infinity in the orthogonal direction. Here you cannot move here. The distance is infinite. But of course, it doesn't mean you cannot go from one point to another one, but it means that if you want to go from one point here to another point, you need to pass through other layers and make a complicated curve somehow. Okay. So that's the only really point that we will use in some sense. And okay, so this structure has been used, as I said, by described and used by geometers and analysts who were studying sub-Riemannian metrics and sub-Riemannian manifolds, and in particular Chitty and Sarti, and also Remco Deutz in Holland, and also Boskane and others have studied the diffusion and curvature motion in this particular topology. And the goal of their work already is so this is something I should have said from the beginning. The main application of this is essentially in painting, or a special kind of in painting. And here what they were trying to do is, given an image with missing parts and structure here, to diffuse this inside the hole by some particular diffusion to complete this structure. And this is perfectly well done by this kind of sub-Riemannian diffusion or mean curvature motion in this metric. They have experiments which really show completion even of crossing structure in a very nice way. Okay, so what we wanted to do is not, I mean, they have very good results. We wanted to adopt a different point of view, which is variational, and to try to understand how the same representation can be used to represent energies on curves, depending on the curvature. So in particular, you'll know that in the 90s, there was this idea that the elastica functional could well close hidden contours, and this was more or less based on psychological experiments of Canissa, and there was all a theory on this, and how you reproduce yourself missing contours in your brain. And this elastica functional is interesting, and it has been studied a lot, not only in the context of imaging, but mostly in the context of imaging and in painting. And it has a lot of problems. It's not easy to discretize or optimize, but it's also theoretically not easy to handle, because it's not really lower semi-continuous, so you don't know if you have minimizers. You have to study some kind of relaxation, and there have been a lot of study about the relaxation of this functional. For instance, you see that very obviously, if you have a shape like this, you don't expect this shape to have finite energy, because it has a cut here which correspond to here you have a curvature which would be essentially 2 pi delta. So a Dirac mass, and if you consider this kind of energy, it's infinite. But if you put another object like that and try to understand what the relaxation here is here in L1, so I consider that this is a set, so a characteristic function, and I consider the relaxation in L1, so approximate this with other sets in the L1 topology. Then you can always approximate this with sets like that, which has finite energy. And in the end, you don't see these singularities, and you get something with finite energy. So one set has infinite energy, 2 have finite in this drawing. So that makes the things a bit complicated to study. And also the minimization is difficult. And in fact, there are a lot of works which do quite good job in the completely discrete setting. So there has been this series of work by Schoenemann, who was a student of Daniel Kramers, and he has done work with Kramers, Cal, Masnou, Simon Masnou. And the idea was to design, to encode this kind of structure with a point and a direction on a graph. So discretize both the space and this direction, and put energies on this graph which penalize more or less the change of direction, and represent the groups, the curves on the graphs, and optimize on the graphs. So what we will do is very similar to this kind of work, but in the continuous setting. There are also recent results by Mirbeau with using also the same kind of metric to compute distance and length, and you can recover in this way geodesic, so you can also compute lines minimizing this kind of energies, these techniques. Okay. So what we do is closest to these two works of Christian Thomas and Benedict Wirth from 2013 and 15. One which is called TVX, or vertex penalization, which is a kind of energy which only penalizes the abrupt change of direction. So it's essentially an energy on polygons which counts more or less, or penalize the number of penalize the jump in the curvature. And a second work which essentially does exactly the same as we did. So called general energies which are convex in the curvatures. So we'll study something a bit simpler, but we could generalize to this kind of object. But what they did was a lifting not only in the space and direction, but also they added a component for the curvature, and then some kind of compatibility condition, which is a nice thing, but it makes your problem even more complicated, because this is already in 3D, so they had to work in 4D, and what we will do is a bit simpler. Okay. So to describe our approach, the simplest way to do is to start with a simple planar curve and to try to understand how you can represent its energy when you lift it in this space. So you have a planar curve, and it has an energy which is integral of f of kappa. And first, what you do is represent it, lift it in this space, but you lift it in a particular way so that it should have essentially, I would say, finite length in that space. So the idea is that if you have a tangent vector here, you lift it with an angle theta. You lift this point at the 8 theta, and this one will be, for instance, here. Okay. This is theta. So the new curve is something like this. I don't know exactly. And the new parameter here corresponds exactly to the tangent of the projection. So what is important when you do that is to observe that the length of the new curve, so this curve was a smooth curve, let's say. You can assume it's a smooth curve with finite length. The new curve still has finite length. But finite length means something here, because as I said, if you go orthogonally to to the direction theta here, the length becomes infinite. The metric is infinite. So the fact I have lifted it always such that the horizontal tangent is the vector here is the reason for which it has finite length. It is admissible in that space. And the length then is very simple to compute because essentially, so this will be gamma, large gamma of t. The length is simply the integral from 0, let's say it parameterized between 0 and 1 or 0 and L, or 0 and L. Okay, so if, and here I have gamma dot equals 1 and L is the length. So the length of this new curve is this object, and this gamma dot is what? It's gamma, small gamma dot, and then theta dot. So this is derivative with respect to the t. So this has length 1, and this is exactly the curvature. So the length is the length here is this expression, and this is 1 plus kappa square. So you see already that when you do that very simple lifting, then just the length here, which is, I will explain, essentially a convex functional, just the length here is already a function of the curvature of the initial function, of the initial curve. It's the simplest one if you want, square root of 1 plus kappa square. So this has been observed already some time ago and used in some calculation. So what we do essentially is generalize that to handle more general functions of the curvature here. Okay, so if we have a more general function of the curvature, the energy here, f of kappa can be written in this way. It's f of, so gamma theta is the theta component, so it's theta if you want, and gamma dot theta is the curvature of the initial function. So now the idea to understand how this can be written in general is to consider an arbitrary reparametrization of large gamma, which I call lambda. Then lambda x, which is the horizontal projection, is the reparameterization of the initial curve small gamma. So I have lambda here, which is lambda x, lambda theta, and this is lambda x. Okay, and the curvature, which is the variation of the angle, is simply here, it's easy to see that it's simply the variation of the vertical component of lambda divided by the length of the horizontal component of lambda, of the variation of lambda. So this expression can be written in this way. Okay. Well, the length it's well known. The length is simply this. So this is the length, and if you have a function of the curvature, then you have to replace this with the curvature and dt with. So I should have written dt with length of lambda x dot ds, and you get this expression. So this is quite simple. But already here you see something which looks like a sort of convex function of lambda in some sense, in some vague sense, which I will make more precise now. And how do you do that? So now to understand how you represent this as a convex function of something, you have to represent your curve by an object which lives in a vector space, and here the simplest way is to represent it by a measure. So the idea is that when you have a curve with a tangent, you can always, and with finite length, you can always introduce a measure which would be tau times the length measure. So this is the Hausdorff measure of dimension 1 on the curve. So this is the curve C. And this is rigorously defined as follows. You have given a function, a continuous function, a continuous vector field. This is defined as the integral on the curve of tau, or if your curve is parameterized, so of tau times phi, the scalar product, the let's say I will try. Okay, I make some confusion here because C is the curve, and C. Let's assume that C is represented by a parameterization gamma of t. So this is phi of gamma of t, gamma dot of t dt, if you want. 0 to 1 or 0 to L or 0 to whatever. So this object defines a measure on a measure in that on the space where the curve is defined. Phi here is a vector field. Okay, and this measure is written in this way: is the tangent times the length measure on the curve. Okay, so it's written here with this particular curve gamma. So here, what I call sigma. Sigma is tau h1 restricted to the curve, and this measure is defined as follows. And if I define this measure as follows, my previous expression here can be replaced by this thing. So now I'm integrating on all omega times S1, but it's a fake integration of omega times S1. It's a measure which is carried by the curve. So it depends only on the values of the curves, of course. So this is 0 everywhere else. And I obtain that the integral of f of kappa is given by a convex function of this measure. And the convex function is precisely this one. So it's h bar of st is s f of t over s. So t is the curvature argument if you want, and s is the length argument. So it's f t over s if s is positive, if you're going forward. It's what I call f infinity, which is the recession function. So it's the behavior at infinity of f. So you see, if you send s to 0 here, you see the behavior at infinity of s of f here. So it's f infinity of t if s is 0, and it's plus infinity if s is negative, so if you're going backwards. Okay. So, and this function, it's well known that it's convex. It's not only convex, it's in fact known to be the support function of the set AB, where A plus f star of B is negative. So it's the sup of AB scalar st, so AB dot st, for all AB such that A plus f star of B is negative. So this is a convex one homogeneous function, which is well studied in the literature. And here you can go a bit further. So this is a convex function of this measure, but here I have sigma x theta, and I want to write this as h of theta sigma. So the way to do that is to observe that sigma x is always a positive measure times theta here, because otherwise the curve is not admissible. Saying that the curve admissible is saying that the x component of my measure is always in the right direction. So it's in the direction theta and it's going forward. So it's positive measure times the direction theta. So if I introduce a function h of theta p, which is convex in p, which is defined as this h bar of px dot theta p theta if px is aligned with theta in the same direction, and plus infinity if px is not aligned with theta in the same direction and in the same direction, then so what I mean is that this will be infinite if you have any object which is in the wrong direction here, and it's finite only if you go in the right direction. Then your integral of f of kappa is simply written as a function of this measure sigma, which is integral of h of theta sigma, and this is convex in sigma. So if you have never seen this, you have to believe me that it's relatively easy to define a convex function of a measure, especially if this function is one homogeneous. It's easy in most cases, but it's even easier if the function is one homogeneous. So I can represent this as a convex function of the measure sigma, which represents the curve, the big curve, the big gamma curve, which is particular convex function. Okay. So now, okay. Now, a last observation to generalize with these two arbitrary curves or arbitrary functions is to observe that this construction, this definition of a measure associated to a curve creates a particular measure because this measure has zero divergence. And this measure, or let's say zero divergence, or if the curve is not closed, then the divergence is simply a Dirac mass at the end minus a Dirac mass at the beginning. It's easy to see from this formula because if this particular vector field is of the form grad psi, for psi a scalar function, then you see that this becomes psi of gamma of t d over dt. This is grad psi of gamma, gamma dot. So this is the derivative of psi of gamma. And in that case, this is simply psi of gamma of 1 minus psi of gamma of 0. So if you define this kind of measure associated to a curve and integrate it on a vector field, you just get, on a gradient, you just get the value of the function at the end minus the value of the function at the beginning. This is exactly saying that the divergence of this measure is the Dirac mass at the end minus the Dirac mass at the beginning. And I think it's minus the divergence. So there is a sign mistake here. Okay, and in particular, if the curve is closed, so if gamma of L is equal to gamma of 0, then the divergence is 0. Or if the curve starts from the boundary of your domain and arrives in the boundary of your domain, and if you look only at smooth function with compact support here, then it's also 0. So the divergence inside the domain is 0. We will restrict ourselves when we generalize only to measure with 0 divergence, which are the generalization of closed curves essentially. And one observation in particular, if your divergence is 0, you can if you have a measure whose divergence is 0 here, you can consider its horizontal part and average it on all the theta, and it's easy to see that the divergence will be 0 here in the plane, because it's exactly as so you see averaging vertically is defining the measure sigma bar, which is defined by this operation. So it acts on a vector field, 2D vector field, exactly in this way. And now if my vector field here is a gradient, then my vector field here is a gradient. It's simply a gradient of a function which does not depend on the last variable. So this is 0 because sigma has 0 divergence, so this is 0. So this, what I call this marginal, so the integration over all angles of sigma x, has also 0 divergence. And in particular, in 2D, you can rotate it and you get a gradient. And what do you do when you do that? You go back from this measure, so the length measure here, so the measure defining this curve here, to this measure here, the measure defining this curve here. So that's exactly what this averaging does. And then you rotate. And when you rotate, you replace this measure on the curve by a measure which is the gradient of the function which is 1 here and 0 here. Which is actually a gradient. It's a gradient of a function with bounded variation, which is the characteristic function of the set which is enclosed here by this curve. So in some sense, the energy I have defined here, I can see it as an energy of the characteristic function of the set here. And then I will generalize to any function. So that's what we have done. So we extend this to any function as follows. So we take any function with bounded variation because we want essentially the gradient to be a measure. And we consider all the, so now we just don't consider only the measure associated to curves. We consider all the measure with zero divergence. And we consider all the measure with zero divergence such that when we average them, we find the gradient up to a rotation of 90 degrees. Okay, so maybe they are known. In that case, the functional is infinite. But you see for the characteristic function of a C2 set, for instance, there is at least one, which we have built. So we consider all these fields, and we measure the energy of this field by this H we have introduced, which is a generalization of the F, which is derived from the F. And we take the minimum value. And when I take the minimum value, we have to do some technical assumption, and the main technical assumption is that F is bounded from below, not only by a constant, but also by an affine function. So that essentially this thing is coercive, because if this is true, then in fact H bar, or H of theta, if you want, is larger than the length of sigma. It means that this expression is larger than the total mass of sigma. And if you have this, then it's easy to see that this is a mean and you can do everything you want. So in that case, otherwise it's very hard to study this problem. In that case, this defines a convex lower semi-continuous function on bounded variation function. And of course, by construction, because this is an inf, and here in particular, if you have a C2 curve, you can put this, the measure corresponding to the large gamma here in particular. So it's easy to see that by construction, you have this inequality, because this is an inf, this is smaller than what we have built here for the curve large gamma. So by construction, we have this, and the only theorem we have in this work is that if we have a C2 set, that in fact this is an equality. And if you think about it, it's more or less obvious. It means that the most economical way to represent this curve up above here is by this trick, is by just lifting the point and the orientation correctly. And if you put more, meaning essentially you could put some parts of curve here which would be cancelled. So in one direction, which would be cancelled in the other direction, so that when you project, you don't see them. So you could do it, but then it will be energetically more expensive. That's more or less what you would do here, what you need to do here somehow. Here, when you represent, you need to lift one part at the level theta and one part at the level theta plus pi, if you want. And then when you average, don't see anything. But but this is not a C2 curve, if you want. But for a C2 curve, you never need to do this, or it's more expensive to do this. So you see that it means that what we have first done is most likely the most economical way to lift a C2 curve. And this is the reason for this theorem. Unfortunately, we never, I still have what, 15 minutes? We never found, let's say I didn't find an economical proof for this simple fact. So I will not describe the proof, which is a bit technical. It's not very complicated, but it's based on a complicated result, which is very natural, which is a theorem due to Smirnov. And it tells you that any curve with zero divergence, any measure with zero divergence, let's say in Rn, but in fact is a superposition of curves representing curves, of measure representing curves. So it's a superposition of curves. So the theorem is exactly, one of the theorems of Smirnov is as follows. He said that if you have any measure with zero divergence, you can see it as a kind of convex combination of measures lambda, which are all of the form of this form here, so which are all one-dimensional measure carried by curves for a particular set of curves. So you integrate, let's say, on all the rectifiable curves, you have a measure on this curve, and sigma is a superposition of these line measures. And the representation is convex or exact or tight in the sense that the mass of sigma is also the average of the mass of these measures. So the length if you want. So this is very natural, but it's not, in fact, it's not true for higher dimensional objects. So that's the strange thing. But this is quite natural. It tells you essentially that if you have a vector field with zero divergence, going from somewhere to somewhere, you can in fact represent it as a superposition of line vector field carried just by a line. And it's an average of such. Okay. So thanks to this theorem, we could prove our result. So I will pass a bit the details. The idea is that we really need to, I mean, it's very important that the decomposition is convex in the sense that you have this, because this means what? This means that you don't have cancellations in this expression. You don't have sometimes in your vector field, you don't have sometimes in the representation on the left a curve which goes like that, which is cancelled by the curve which goes like this. Because if you add this, then you would have extra mass here. You don't see. You would pay for this mass plus this mass, and you don't see this mass in the end. Okay, so that's the most fundamental point, if you want, that this decomposition is convex and tight. So because for this, from this fact, then it's relatively easy to show. It's a bit technical, but very easy, in fact, that almost everywhere in the sense of this measure, for almost all the curves in the representation, then the orientation of the initial measure is the orientation of the curve. And this is very important in our setting because it tells you, because we look only as measure. Okay, we look at measures which have finite energy here. If the measures have finite energy, it means that at each point of omega times S1, their orientation is given by the theta variable. Otherwise, they would not have finite energy because h is infinite if you go in another direction. But since the decomposition of Smirnov is tight, it implies that if you take any measure with finite energy, if you consider the curve which passes through the point here in the Smirnov decomposition, then the curve also will have the same direction. And that's the most important point, if you want. So this measure and this curve measure have the same direction. It means that almost all these measure lambda correspond to curves with finite energy, which are oriented in the right way. And in particular, when you project them vertically, they correspond to curves whose orientation cannot vary too widely because they are rectifiable curves. They are curves with finite length in that space. And it means that their last variable, which is the orientation of the projection, does not oscillate too much because otherwise they would not have finite length. So it means essentially that if you want, this quantity must be finite for all these curves. Because this quantity is the length in the lifted space. So it means that their orientation has bounded variation, if you want. So you could have kinks, but you cannot have big oscillations. So these curves are quite nice. And if these curves are quite nice, we can look at their intersection with the initial boundary of the T2 set we were starting with. Because our initial goal was to start from a C2 set and try to show this. And the idea is to start with a measure with zero divergence and to show, so since we already have this inequality, the idea is to start from a measure with zero divergence and show that this quantity is always larger than that. So we start with a measure with zero divergence, we decompose it into curves, we look how these curves intersect with the initial C2 set, and if you study this a little bit, you see that when the curves intersect with the initial C2 set, then the curvatures coincide. So the curvature of the projection, which is a bounded variation, which is a measure essentially, almost everywhere on the boundary of the C2 set is the same as the curvature of the C2 set. And that is enough to say that the integral of h of theta of lambda, which is essentially integral of f of the curvature of lambda, is larger or the same as integral of f of the curvature of the set, because they coincide. Okay, so that's the conclusion. So the idea, so more technically, we look at the points where the projection of lambda and the boundary of the set not only coincide, but they have the same orientation. And here we see that the curvature kappa, which is a measure, coincide with kappa E almost everywhere. And by definition of f and h, we can deduce this inequality so that the integral of f of kappa A is a part of kappa, but is less than the integral of h of theta and lambda. And since this is the curvature of the C2 set, we find that the integral of the curvature of the C2 set is less than this quantity. And this requires to reintegrate on all the lines defining sigma. So this is a small technical part. What I don't like in this proof is that it looks a bit complicated. It's not so complicated, but you need to take into account all these general measures which should cancel in the end. And obviously, you know that you're wasting your time because it's obvious that they make a larger energy. So maybe there is a simpler way to do that. Okay, so let me finish and pass to numerical examples. To conclude with this result, it's very likely that there are more situations where the two functionals coincide, in the sense that I would expect, for instance, that if you take a bounded variation function such that all the level lines have are C2 if you want, but not only this, if you find that you need that the curvature is globally a continuous function. So for instance, it's not true if you have a parabola, because here the curvature goes to infinity, but you can design functions for which all the curvature all the level lines are C2 and globally the curvature is continuous. I think that this should be true in that case, but I don't know how to prove it. And you also can check what happens in these situations. So in this situation, I expect that we get the same relaxation as this drawing, essentially because the measure is lifted, if you want, in this way, more or less. But there is a nice situation where we know, and this was already observed in the paper by Christian, Benedict, and Tom, when you know that this is not true, it's if you have this, but also this. Because from the point of view of this lifting, then you can lift this curve as this curve in the omega times S1 space. And then for the rotated by 90 degree, you do the same, but you have a curve which is just shifted by pi over 2. Okay. And so that the energy of this should be just the sum of the energy of that twice, if you want. But from the point of view of the L1 relaxation, then you cannot do that, because it would mean that you are approximating this set with this and this set with that. But here you're introducing infinite curvatures. So from the point of view of L1 relaxation, this is the way you should do. And you get a higher energy. So the energy we define is below, I think, is below the standard L1 relaxation, which doesn't mean it's better or worse. It's different. In that case, it's a bit complicated to understand what you would like to do. Okay. One point, I will skip that. One point is that we computed also a dual representation because it's a convex functional, so there is an easy dual representation. It's funny to see that the dual representation looks a lot like standard definition of the total variation. So it's a sup of psi du for psi vector fields with some condition. But of course, the condition is much more complicated and involves f than the definition of the total variation, for instance. And what is interesting in this formula is that is how we discovered that our energy was exactly the same as the one by Christian and Thomas. and Benedict, because they also had dual formulation, and we found that they were the same. So now for the numerical discretization, we tried many different approaches, and the difficulty is to represent sharply measures by finite differences or finite elements. So right now the best, it's not the end of the story, but that's what we found is to use a staggered grid for the image and the field. We have, let's say, a justification of the soundness of this approximation up to a small, let's say it's 100% justified in the case of one Lipschitz functions, and otherwise you need to smooth a bit your problem. But if you do other approximation, it's very diffusive. So let me show a few examples and then finish. So first, to see a bit the behavior of the functional, we did just basic denoising experiment, so shape denoising with. So this is very stupid. We use this function f of du as a regularizer, f of u as a regularizer, and we put a L2 penalization on the characteristic function of this set. And we tried with essentially 1 plus modulus of kappa and 1 plus modulus of kappa square. And here you see that there are small differences. For instance, for 1 of modulus of kappa, you see there are a lot of sharp angles, which are admitted because they are just a jump in the curvature. And for kappa square, everything gets much smooth. You still see a small phenomenon like this, but they can be represented in this way. So it's normal that you would have some cusp, but probably this cusp goes through up to one of these cusps, for instance. And then you get something very smooth here, while here you still get something piecewise smooth if you want. Okay. So one one goal of this is to be able to do some kind of in painting with the elastica, so connect orientation by smooth curves. And you can see here, so this is a variant of Weikert's experiments, but he has a cat and we had a rabbit. Where we selected just a few points where the orientation is really changing a lot or things like that. And by only these few points, you can reconstruct the initial shape. This is with the elastica. So that's a nice justification of the use of the elastica for some kind of shapes, for simple rabbit shapes, let's say. So here is another application which is more interesting somehow. It's an image with lost parts, but okay, not very big parts, small parts. And if you just do a total variation in painting, obviously it doesn't work very well, because here, for instance, you have long structures, and with the total variation, it's shorter to cut them than to extend them through the gap. While if you penalize the change of orientation, then it becomes very expensive to cut them, and much cheaper to continue them, because you don't change the curvature. So this is a really striking example. There is another example which works a bit less, because we lost a lot of lines. We kept very few lines here, but here with the total variation, you see it's a disaster, while still you can find back something with this thing. Okay, so here we tried also to understand what happens when we complete a disk, and that's where you see that we still have progress to make, because it works, but we still have a lot of diffusion, and the optimization is not very easy, because this is with the essentially with the total curvature, so this should be very close to that. In fact, it should be the same, I think, these two, normally. Because the total curvature is 2 pi anyway, and it's essentially the length which should dominate.
The middle image is 1 plus curvature squared.
This one and this one?
Elastica.
This is one, and this is, okay, so I'm sorry. I'm sorry, so this was a misinterpretation of the experiment. So this is, okay, so this is wrong, this is 1, okay? This is epsilon squared, and this is 1. So this is when you penalize more or less the length. But it's very hard, as I say, it's hard to penalize only that, because you have a loss of coercivity, so we need to put some. And here it doesn't work so bad. It's a bit diffusive, but we almost get the circle, so I think it's a good experiment. And this is how the disk is represented by in the rotor-translation space. So you see that the field is quite concentrated still on the boundary, so it doesn't work too bad. Okay, so I will finish. I still well, okay. This is a curvature flows which you can compute with the same. And to conclude, so the idea here is that we have introduced some systematic way to represent energy of the type f of kappa with f convex, which is a variant of this work of Thomas Benedict and Christian. We still could extend the family of functions for which the relaxation is tight. We can still try to improve a bit the discretization, but it's hard. And thank you very much.
Thank you very much. We have time for questions. There's already one.
In your experiment with the disk completion, you saw that there are some dissipative artifacts. You still have some sort of blurring, which is normal and fairly common for anisotropic strategies. Do you have any ideas how this could be reduced?
Yeah, that's one of the things we're really working on. There are two strategies. One very complicated, which could be to work with special kind of finite elements where you reduce the diffusion, which I don't know if it will be very easy to implement, and another which already have been implemented by Thomas and Christian and Benedict, which is to represent the measure a bit differently with line. So to represent line measures with lines. So you discretize somehow lines in this omega times S1 space, and you try to use only these measures. So this restricts a lot the orientations. It's even it's in some sense a mix between the discrete approach of Schoenemann and other and this continuous approach. And this gives sharper results, but with less orientations. And it's hard to get everything working at the same time.
Another question, yes?
In your painting practice, do you have an error estimate?
No, not yet, I would say. No, because I mean, we have some kind of error estimates in between the discretization, at least for this kind of functional. Otherwise, it starts to be complicated. Between the discretization and the continuous energy, but they are very bad.
Not between the impinging function and your original.
No, this is not. Well, I don't think this is very. No, we could hope to have error estimate between our drawing and the true C2 curves, which minimizes the energy. But this is possible, but it will be very bad estimates, like discretization to 1/4 or something like that. So.
Okay, two more questions.
You studied from some group of transformations, and then you initially came to curvature. If you add zoom, so you're supposed to get curvature derivative, right? Does it make sense to consider such things?
That yes and no. I think it would. I think you could try to look at more complicated representation. But one thing, for instance, I didn't say is that you could hope to extend this kind of stuff to higher dimension, for instance, for surfaces. But you see, for surfaces, you will be working in dimension 5. So it will be completely intractable to do computations. It's already difficult here. So we could try to do it, but we would not really be able to see the results and see what it gives. And also, if you add some more groups, that's this difficulty. The question would be how to add more information and keep simple so that you can still do some calculation. And this I'm not sure. So we did not think too much about that. That could be interesting, maybe to just add one parameter. I don't know.
There's one more question. Yes.
This theorem of Smirnov, is it related to Croft's formula?
I think it's no. I think it's simply it's more. It's a more simple thing. I mean, there is a topological difficulty in the theorem of Smirnov, but basically, if you just consider it naively, it's simply saying that you see these fields with zero divergence are essentially the convex envelope of the curves. So it's simply a convex representation. It's It's just a kind of Klein-Millman theorem, I think.
Okay, so
We can discuss that
Yeah,
later, because I think
you
it's
concluded something.
I think it's simpler, but maybe I'm wrong. It's not a simple theorem. The proof is not simple, but I think the idea is simpler.
Okay, so this is certainly a lunch topic, perhaps. Yeah. Well, before we go to lunch, actually, I would like to thank the speaker once again. Thank you very much.